Look around you. Everything you see, from the screen you're watching this on to the orbit of the planets, follows strict, invisible rules. But here is the strangest part. The rules governing our physical reality are written in a language that humans invented in our own minds. That language is mathematics. Why should abstract structures, born in our thoughts, so precisely mirror the structure of reality itself? It is one of the most profound mysteries in science. Physicist Eugene Wigner famously called this the unreasonable effectiveness of mathematics. He noted it was something bordering on the mysterious. Wigner even went so far as to say there is no rational explanation for it. Today we're going deep into this rabbit hole. This isn't just a recent discovery. From the ancient Greeks to Newton, we've used math to describe motion and gravity. But modern physics reveals something even more uncanny. Math doesn't just describe what we see, it predicts what we don't yet know. Take James Clerk Maxwell in the 19th century. He was working with purely mathematical formulas for electricity and magnetism. Through pure mathematical manipulation, Maxwell derived a wave equation that predicted electromagnetic radiation at a specific speed. That speed was precisely the speed of light. His math revealed that light itself was an electromagnetic phenomenon before we could even prove it. Then there's Paul Dirac. In 1928, he was trying to describe the relativistic electron using a new equation. His math gave him an unexpected result: solutions for negative energy states. Most would have dismissed this as a mathematical error. But Dirac trusted the math. He predicted a new form of matter with opposite properties, antimatter. 4 years later, the positron was discovered in a lab. The abstract formalism had revealed a hidden part of our physical reality. Finally, consider Albert Einstein. In 1915, he rewrote the rules of the universe with general relativity. He translated gravity into geometry. In his math, mass doesn't pull, it curves the very fabric of space-time. From these geometric equations, scientists derive the existence of black holes, places where math says light itself cannot escape. For a century, black holes were just symbols on a page. Today, we know they are a massive reality. Einstein's math also predicted gravitational waves, ripples in space-time that weren't detected for exactly 100 years. In every case, the math didn't just organize what we already knew, it led the way to discoveries we couldn't even imagine. This leaves us with a fundamental tension. Is mathematics just a tool we invented, or is it the fundamental blueprint of existence? Some believe the universe doesn't just follow math, it is math, a physical manifestation of a mathematical structure. Others suggest our minds are simply tuned to the frequency of reality. But both explanations still leave us in awe of the connection. If we cannot explain why math works so well, we leave a massive gap in our understanding of the world. Mathematics isn't just a subject, it's the secret code of the cosmos, waiting for us to decipher the rest of it. So how do we explain this? 4 primary explanations have emerged. Let's break them down. The first and most radical response to Wigner's puzzle is to deny that there is, in fact, a puzzle at all. How? By reinterpreting the ontology of physical reality itself. Physicist Max Tegmark advanced the mathematical universe hypothesis. He proposed that the universe is not merely described by mathematics, but is, fundamentally, a mathematical structure. According to this view, physical systems are mathematical objects. Under this interpretation, Wigner's puzzle dissolves because mathematics describes the universe perfectly. It works because the universe is mathematics. Physical objects are not material things that happen to obey laws. An electron is not a thing that follows a wave function. It is a wave function. While this view resolves Wigner's puzzle elegantly, it raises profound questions. Why should abstract mathematics have concrete instantiations? Why are some structures actualized while others are not? A contrasting explanation proposes that mathematics appears effective not because the universe is inherently mathematical. Instead, humans selectively study phenomena that are amenable to mathematical treatment. The selection bias is human, not cosmic. Scientists choose to study phenomena that are measurable, repeatable, and quantifiable. We ignore or marginalize aspects of experience, like subjective qualities, meanings, and purposes, that resist mathematical formalization. In this view, mathematics is not revealing hidden truths, but is merely a map we construct to navigate specific phenomena. However, this view struggles to explain why mathematical predictions often succeed in domains not yet empirically explored. Our third perspective emphasizes biological evolution and cognitive development. The claim is that human brains evolved in this universe and developed cognitive structures that resonate with the structure of reality. Organisms that survived possessed capacities for tracking spatial relationships, predicting trajectories, and recognizing patterns. As these cognitive structures evolved to match the environment, the mathematics we invented naturally resonates with it. We are recognizing patterns in math that mirror patterns in both our cognition and the universe, because we evolved within it. Mathematical effectiveness reflects a deep alignment between brain structure, math, and reality. We have co-evolved. Finally, a contemporary explanation proposes that mathematics is fundamentally a language for compressing information. The universe exhibits patterns, and mathematics is simply the natural language for expressing compressible patterns. A random universe would be incompressible. But our universe exhibits regularity. It has laws. Math is the language for that regularity. We observe a mathematical universe because only in law-governed universes could observers arise to study mathematics. 4 radical views on a profound mystery. Which one resonates most with you? All 4 explanations capture elements of truth, yet each leaves something unresolved. The most difficult mystery to explain is not merely that mathematics works, but that it so often works before we need it to. Abstract mathematics, developed centuries before any application, suddenly becomes central to understanding newly discovered phenomena. Consider complex numbers, developed in the 16th century but dismissed as formal manipulations until they became essential to quantum mechanics. A profound reframing emerges. We often ask, why does mathematics describe nature? But we might reverse the question. Why does nature conform to mathematics? Why should the universe care about our mathematical formalisms? What if mathematical structures are more fundamental, and physical instantiation is just one way mathematical possibility manifests? Under this view, the mystery is not why math describes nature, but why certain structures are physically instantiated while others are not. And this brings us to the most mysterious connection of all, consciousness. Human consciousness appears capable of grasping abstract truths. We understand that 2 + 2 = 4, not through empirical observation, but through pure, abstract reasoning. This generates a strange circularity. Consciousness recognizes the mathematical structure of the universe from within that very structure. Why should the brain generate consciousness capable of grasping mathematics that describes the very universe it is a part of? Some philosophers suggest this points toward a deeper unity, where consciousness, math, and reality are manifestations of something more fundamental. After a century of analysis, we possess not one answer, but multiple complementary perspectives, each capturing elements of a complex truth. At the pragmatic level, mathematics is a tool we have developed to solve human problems and study amenable phenomena. Cognitively, our mathematical intuitions work because our brains evolved in this universe and reflect its regularities. At the structural level, information theory reveals that math is fundamentally about expressing compressible patterns. And at the deepest level, mathematical realism suggests that mathematics may reflect something fundamental about reality itself. Together, these suggest that the unreasonable effectiveness of mathematics points toward a deep relationship between consciousness and abstraction. The universe appears mathematical because consciousness evolved within it, and math is the natural language of patterns. This puzzle cannot be resolved alone. It demands the integration of physics, philosophy, neuroscience, and epistemology. It teaches us something not just about math or physics, but about the fundamental structure of inquiry and understanding itself. So next time you write an equation, remember, you aren't just writing symbols. You might be speaking the native language of the universe. Is math invented or discovered? Let me know in the comments. Thanks for watching, and I'll see you in the next one.